All right, let's begin. So the question here, number 15, is a ball thrown vertically upward returns to the thrower's hand. Which part of the journey requires a longer time, the upward or the downward? You have to answer this if there's no air resistance and if there is air resistance. So clearly, well, maybe not clearly, but do you get the impression that the answer would be different? Would it be the same? Okay, so let me just draw this out here. A ball thrown vertically upward returns to the thrower's hand, so I'm just going to draw the traditional stick person. And I guess I should probably leave room for the ball to go up. Okay, so the question is, which part of the journey requires the longer time, the upward or the downward? So T up or T down? What is your gut telling you? It should be the same, right? Is the distance the same? Is the acceleration the same? Why is it the same? Gravity's the same whether it's going up or down, right? We showed that when we did the ramp thingy, right? The acceleration is minus 9.8 whether it's going up or down. And there's an initial velocity here, and I think most of you realize that the final velocity over here, those two numbers should be the same, just one's up and one's down, right? One's positive and one's negative. So I think you should get that the overall time should be the same, should it not? Like if I go A equals delta V over delta T, right? What's the velocity right here? 0, right? So if the acceleration is the same, it remains the same. Is the delta V, does the change in velocity from there to there the same as from there to there? The change in velocity? Like if I throw it up at, say, 5 meters per second, it goes from 5 to 0, and then I lay back down, it's 0 to 5. So numerically, the change in velocity is the same. The acceleration is the same, so what else has to be the same? Time must be the same. Time up must equal time down. All right. Now, I have to be careful here. On the way, if there is air resistance, and there always is, right? Does the answer change? No, Carolyn? Why not? Maybe. And this is not an easy question. I always have to look at my notes to make sure I get it right before I explain it. So it's not easy. All right. Go ahead. Okay. Like your gut's telling you it should be the same, right? Yeah, because we've been taught that all along, that kind of stuff, right? But usually we sort of deal with this stuff in the non-air resistance world, right? Things change a little bit. Here's what I'm going to do. I'm going to draw for you with air resistance when the ball is going up, okay? Which way is gravity? So I'm going to write acceleration G is down, right? Which way is the acceleration due to the slowing down due to air resistance? Is it not also down? Right? There's a little bit of air resistance. I'll go AA for air resistance. Okay? So what would be, let's say the air resistance is, say, 0.2, then my overall acceleration would be minus 9.8 and a minus 0.2. I'd have an acceleration of minus 10. Does that sit okay with you? Right? Like it's slowing down a little bit faster because of air resistance. Right? Like if I take a piece of paper and I throw it up, the air resistance on it is significant, right? And it slows down faster, right? Okay. Now, what about, this was on the way, this is on the trip up. What about on the trip down? Which way is the acceleration of gravity? Down. I asked you the easy question first. Which way is the acceleration due to air resistance? Up. Up. So my overall, my net acceleration would be minus 9.8, right? But the 0.2 is? So in fact, I've got an acceleration of minus 9.6, which is different. So if it doesn't accelerate as fast, or if it doesn't slow down as fast on the way down, right? then what would happen to the speed? It would have to be going a little bit faster, right? Which would mean the time would have to be a little bit shorter. A little bit shorter. And that's kind of counterintuitive. Okay? And it's probably okay if you don't get that first crack. That's kind of something you got to sort of really sort of look at, think about, kind of let it percolate for a day or two. Okay? I'm not 100% sure that I get it. So let the gears turn on that one, but I think that makes sense. Okay? I'll leave that up there for you to. I'll post it as well for you to think about. Okay. So 16, an object that is thrown vertically upward will return to its original position at the same speed as it had if air resistance is negligible. If air resistance is appreciable, will this result be altered, and so how? And it's exactly the same question, right? Will the speed be different if air resistance is more than negligible? We already came up with the speed here will be what? A little bit faster. Okay? The coming down will be a little bit faster if there is significant air resistance. Now, obviously, if the air resistance is to the point where it reaches terminal velocity, then it's different too, right? Yeah, lots of different things going on. All right. Do I really need to do 17 and 18, do you think? Like, what are we talking about here? 17, I'll just quickly have a look at it. 17 is a position time graph, right? Oh, by the way, some of you, more than a few of you, still owe me an assignment, which was due on Wednesday, according to Adam's sheet, because you wrote it down, right?
Just the data.
Oh, really?
Yeah. I don't know if it's due there.
Okay. Was it due Tuesday? I think you might be right, yeah. Yeah. So I guess, yeah, it's due today, isn't it? Yeah. Now, I gave you till Friday, right? I gave you till Thursday? This Thursday or last Thursday? Did you get it in? Because I have Jesse's. Well, that's a problem then. Because if you haven't handed it in, then that means that I don't have it.
Memo who you got?
I got Jesse's and Corey's. And by the way, I posted this last night. Adam, and Parker, and Carly, and Natalia, and Chris, Justin, and Lindsay, and Courtney, and Darren, and Troy, and Hunter. And if I don't get it today, then that means you got to do the alternative assignment. I see that. Thank you. And we don't want to start that again, do we? All right, so this is a position time graph here, right? And so what's happening here? Constant velocity here. In fact, you might have just wrote right on the graph if you did the question. Constant velocity there. Increasing velocity there. Slowing down there. Momentarily paused at the top. And then speeding up backwards. Right? And doesn't actually sort of flatten off there, does it? Okay? So I'm hoping that if you A, didn't do that, at least you understand that. That's ultimately what you got to do. (18) Describe in words what's happening here. This time it's a velocity time graph. Describe in words the motion of the object, graph, figure 224. Now this time, because it's velocity, what's happening? I guess I need to draw it first. Something like that, right? All right, so what's actually happening here? If you assume it's a straight line, it's actually slightly angled. That's it. That's increase in velocity. So what does that mean? Speeding up, accelerating, right? Right? And what's happening right here? Ooh, this is a good test question. What's happening right there?
Constant velocity.
Constant velocity. It's not stopping, is it? Right? It should be constant velocity, but only for the briefest amount of time, right? In fact, it's hardly flat at all. And then it comes all the way back down to 0. And so this entire trip is, in fact, slowing down, isn't it? And right down here, here it is where it is stopped. Why is it stopped right there, Chris? It's at 0. And then speeding up again here. Okay? Excellent. All right, now I probably should have warned you that you're going to need your textbooks today. Fortunately, yours truly typed out the example, so they're on that sheet that you've now got. So I would like to do some textbook style questions. You don't actually need the questions right. Questions right. Give me a second to get this up. All right, so Troy has pointed out that we have the quadratic formula on there. We also have v equals d over t, a equals delta v over t, vf equals vi plus at, d equals vit plus a half at squared, vf squared equals vi squared plus 2ad, and my all-time favorite, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Although you'll notice that the square root somehow didn't quite make the grade here. Not sure what happened there when it got converted. Anybody in here not familiar with the quadratic formula? Anybody never seen it before? No? Okay, I'm going to have to come see you guys. But very quickly, when you've got an equation like y equals ax squared plus bx plus c, and I'll just give you a quick example, like y equals 2x squared plus 4x minus 9, and I'm not even sure if that's factorable. The a is equal to the 2. The number in front of the x squared is the a. The number in front of the x is the 4, the b, sorry, and the number all by itself is the c. Okay? And remember, to solve a quadratic equation, what does that mean when you solve a quadratic equation? What does that mean, to solve it? It means to factor. Really what you're doing is you're finding the points where it crosses there, right? The zeros, remember that? It's all coming back to you now? A little bit? Okay. And yes, the answer is we will be doing that. Okay? But I will start you with an easy one. Let's start with an easy one. Kitty O'Neill, a female dragster, reached a speed of 628 kilometers per hour from rest in 3.72 seconds. That's cooking with gas. It's a dragster. How far did she travel in that time? If it's in a book, it has to be true, Justin. Yeah? All right. What's the first thing we need to do? What's her initial velocity? What's her final velocity? 628. But that's measured in kilometers per hour, and the time is measured in seconds. So my distance is either going to have to be in kilometers or meters. Which is the more appropriate unit, do you think? Kilometers or meters? Probably meters. Which means I should probably take the 628 and do what? Convert it to to meters per second, right? So I'm hoping you remember how to do that. 628, the magic number? 3.6. So that's 174.4 meters per second. 174 meters a second. That's fast.
Not real.
It's not real? Now what? I want to know how far did she travel. So which one has D, VI, and VF in it? And T. I've got a T as well, don't I? My time is 3.72. So which one has D, VI, VF, and T in it? All of them are going to need a what? I need acceleration. I can't do anything until I have acceleration, can I? So my next step is clearly to do acceleration. So I'm going to go A equals delta V over delta T. If you want to write it as VF equals VI plus AT, that's just dandy too. So now what's my change in velocity? I go from 0 to 174.4. So my my change in velocity is 174.4, and my time is 3.72. So it gives me an acceleration of 46.9. 46.9 meters per second squared. And now I can do, which one do you think? Which one should I do? Does it matter? D equals VIT plus a half AT squared, that'll work, right? Or VF squared equals VI squared plus 280, that'll work as well. This one's probably better because it's got the D out in front, although it really doesn't matter. So 1/2 of 46.9, T squared is 3.72 squared. And I get 324.3 meters, almost, well, a little over a third around the track in about 3.72 seconds. Let's have a look at example number 8. Maybe you guys could even do this one on your own. No?
You can do it.
No. A Ferrari moving at 20 kilometers an hour, is that believable,
Yeah.
Justin?
Yeah.
I doubt it. Ferrari's go faster than 20. Accelerates to 230, that sounds more like it, in 7.5 seconds. As it does so, it covers an unknown distance. Find the distance covered. This seems to be almost exactly the same as number 7. What's the one small difference? It has an initial velocity. Right? So, what is that initial velocity? It's 20, which we now know has to be converted, right? So divide that by 3.6. Do the other one by 3.6 as well. And I get 5.6 and 63.9. And now follow those steps, same steps, right? A equals delta V over delta T. Now my change of velocity here, you know what, let's write it this way. Let's write, just for fun, we'll write it a little differently. VF equals VI plus AT. It's basically the same formula. Final velocity 63.9. Initial velocity 5.6. Solve for acceleration. Time is 7.5 seconds. So you get a time of, sorry, an acceleration of, not a time. Acceleration is 7.77 meters per second squared. And then you can go and do the D equals VIT one.
How the heck do you get?
I got 260.8.
That's 220.
260.5 is certainly close. It's probably got to do with the 7.77, the rounding and stuff like that. Okay? And again, I'm not worried about the number being exactly perfect.
How'd you get that acceleration? Seems wrong.
Does it?
Yeah. Doesn't the other way. I got 28 meters a second.
No, that's not right. Go away.
260.5 feet. 230 minus 20 is 10
Oh, but you gotta do this in meters per second.
Yeah, that wasn't even.
You can't get in meters per second. How much do you think that would be worth? Probably 3, right? 1 for doing this, 1 for doing this, 1 for doing that, 1 for doing that, right? And the order matters, right? The organization of it matters as well. Question around?
I was off by 0.3%, or 0.3.
Is that close enough, do you think?
I don't know if that's enough.
Absolutely. Absolutely. In fact, I used a different formula to get that 260.8. I bet you if I use this one, I'll get your number. So I just didn't have it for that. So. All right. Well, let's now. Actually, number 10 isn't bad at all. In fact, I think you can do number 10 on your own. The only thing is, it says, oh. Are you asking me? Oh, there is no number 9. Well, My number 9 says find the acceleration of the Ferrari, which you kind of need. I'm not sure why, yeah, stupid textbook. Yeah, example number 9 is find the acceleration of the above Ferrari. I'm not sure how you would do number 8 without the acceleration. Let's go to number 10. Calculate the acceleration of an airbag if it deploys in 30 milliseconds. Justin, do you think that's a reasonable number, amount of time? 30 milliseconds?
Yeah.
Yeah. Well, it's obviously less than a second, right? So we're in the right ball.
Yep.
And moves out a distance of 40 centimeters. Now, does your gut tell you that the only real difficulty here is the units and having to make them work? Okay, so that should be the first instinct. You go, oh, hang on here, I got milliseconds and I got centimeters and this doesn't look good. Okay, millisecond you should realize is a thousandth of a second, right? So 30 ms, milliseconds, right, is equal to, divide that by 1,000 because milli means 1,000, right? So that's going to be 0.03 seconds. 0.03 seconds. And 40 centimeters, divide that by 100, is clearly 0.4 meters. And now we're dealing with meters and seconds, and now we should be okay to just go like this, right? But we want to know the distance, though. I got to have something with, I've got distance, I've got time, and I need to find acceleration. So T, D, and A, this is the one. BIT plus 1/2 AT squared. So I got 0.4. Now, what would be the initial velocity of this airbag? What if the car is moving? You're right, it doesn't say it is. Would it be any different if the car is moving, Chris?
Yeah.
The car is parked, somebody pops it in the hood or whatever, airbag blows up. Or you run into a deer or something rather and the airbag blows up. Would that acceleration of the airbag coming out, would that matter whether the car stopped going 50 or going 100? You don't think it would matter? And that 40 centimeters, now, what is that distance? Is it like, if I'm moving, the airbag goes 40 centimeters this way, but clearly if the car's moving, I'm going to go more than 40 centimeters forward, right? So what is that 40 centimeters? It's just this distance here, right? Yeah, so in other words, it doesn't matter. I'm sort of messing with you here a little bit. So yeah, it doesn't matter. So in fact, the initial velocity is equal to 0. So 1/2 acceleration, time is 0.03 squared. I hope you can solve that. Do I need to go through the steps of that, maybe? Maybe I should, just in case there's someone out there that's having a little trouble with that. I'm talking over here, okay? Never mind that. So I've got 0.03 squared, and I got to divide that by 2, so I'm going to get 0.4 is equal to 0.00045 A. So A is 0.4 divided by 0.00045. And does your instinct tell you that A should be a really big number? I hope so. Did you get 888.9 meters per second squared? Yeah. Do you think that's a reasonable? That seems awfully fast, doesn't it?
Well, it's in 30 milliseconds.
Yeah? Okay. Now, I would like you to try example number 11 on your own, okay? Work with the person beside you. Try number 11 on your own. How much space do you guys have? Do you have a fair bit there? Okay, you got half a page. I will tell you this. If you take care, you should be able to do it on the left-hand side. Okay, so draw a middle down the middle. I'll draw a line down the middle. I'm losing it. Draw a line down the middle. I'm still thinking about Mitt Romney in this. I've got to watch Letterman tonight because I know that's going to be on. Try it on the left-hand side, and I'll give you like 3 minutes. Then we'll do it. 3 minutes. What'd you get, Chris? 3.5 seconds? We got 3.55 seconds. Just Darren? Adam too? Nobody over here?
I got
3.16. I got minus 33.5. Let me show you. All right, so I've got an acceleration of 0.2. I don't think she's much of a spy. She's not going to really last very long if she's only got an acceleration of 0.2 meters per second squared. And her initial velocity is 3 meters per second. How long will it take her to travel a distance of 12 meters? So the d is 12. That's all I've got, right? And I'm solving for t, right? So you should realize I'm going to have to go d equals vit plus 1/2 at squared. I'm just going to drag that whole thing over a bit. There we go. And the distance is 12. The initial velocity is 3 t plus 1/2 of 0.2 t squared. And this does not look good, does it? 0 equals, well, let's put all the t squareds out front. Half of 0.2 is just 0.1 t squared plus 3t minus 12. Is that what you did? And then did you curse because you realized that you're going to have to use the? I took the 12 and put it over here. But how did you do it, Chris?
What we did is, we did it in 2 steps. We did the df squared equals vi squared plus 2ad.
Okay.
We found df, and then we did the df equals vi plus at.
Oh. Okay. Well, I'll show you this way too. Okay. So you need me to explain how I got to this step, Lindsay? I took the 12 to the other side, it becomes negative, right? I leave the 3t, and 1/2 of 0.2 is 0.1, and I just arranged it so it's t squared, t, and then no t, right? And now I'm going to use, because I love using the quadratic formula. So that's going to be t equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Makes me seem smart. Which is the b? B is always the one that goes with the letter by itself, so it's going to be minus 3 plus or minus square root of 3 squared minus 4 times the a value is 0.1, and the c value is minus 12. And that's all over 2 times a, or 2 times 0.1. And you end up the next step showing minus 3 plus or minus, when you take 3 squared minus 4 times 0.1 times minus 12, you shouldn't take the square root of that, you should get 3.7 all over 0.2. And do you guys know what that means, that plus or minus stuff? Right? Like you have to take minus 3 and you have to add 3.7, and you have to take minus 3 and subtract 3.7, and that's how you get the two different values. You should get a minus 33.5 as one of your values. Or there's another value of 3.5 seconds. And the reason I chose it to do it this way is because I need you to know that in a case like this, you might get 2 possible times. What does minus 33.5 seconds mean? Well, in the real world, it doesn't mean anything. Right? But because it's a quadratic, that's why you get that. So what does that really mean? It means if you'd gone, she was starting at 3 meters per second, right? And if she accelerates at that, it's like, how long did it take her to travel the first 12 meters, like back in time, before we started carrying? Okay? Now, there are some times when the time, there's 2 positive times, and you've got to be able to deal with that. And that's why I threw that quadratic. I'm going to stop for the day, Joe, because I know when your brain is full. Is your brain full? Okay. And I also know what's coming up, because Fred and Marnie are coming up, and they are challenging. Fred and Marnie, Flintstones, and Rebels. They're playing a game of chicken. So what I'm going to do is I'm going to give you some time to do some problems. I'm going to do the 2 more harder problems tomorrow. I'll give you some more time to work. Okay, we are almost on this part. We're gonna be moving into vectors real soon. Okay? So take some time to do a couple problems.